Okay, so today I wanted to continue the topic of Quillen injunctions. And derived functors. So today we will mainly focus on two topics. So the first part will consist of discussion on derived adjunctions. And in the second part, we'll discuss Quillen equivalences. Okay, so first let me briefly sketch what we're trying to do here. So as usual, assume that we have Quillen injunction between two model categories. So usually denote it like this. And assume that we have a pair of approximations for this adjunction. So we have one approximation from the left, Ka, and one approximation from the right. Then these approximations induce an adjunction between homotopy categories of respective model categories. So since K and K prime are homotopical functors, they descend to homotopy categories of model categories. And thus we have an adjunction here like this. This is the first part, I think. And the second property is that that F1 prime and F2 prime be a pair of composable Quillen injunctions and then in fact the composition of derived adjunctions is isomorphic to the derived adjunction of the composition. So to make this statement more precise, we need to work a little bit, but the idea is that we can take any approximations, take their derived adjunctions, and what we obtain is the same as derived adjunction of composition of approximations. Okay, so that was the idea of this part. Now, let me discuss in more detail induced partial adjunctions. So assume that we have a Quillen injunction And for any pair where X is a cofibrant object in M and Y is a fibrant object in N, induced junction isomorphism is compatible with homotype derivation. And basically what we have is it's denoted by phi large. So we have an isomorphism of Hom sets like this. And this isomorphism agrees with the relation that certain maps are homotypic, since we assume that X is cofibrant and Y is fibrant, and F and F prime are Quillen functors. There is no distinction between right and left homotypic Hom sets. So yeah, you basically can say that if a map is left homotypic to another map, it is right homotypic. So, since this isomorphism agrees with the homotype relation, it follows that I induces partial junction isomorphism. It looks like this. And this isomorphism is natural in both arguments. Additionally, we have that if we have a pair, if F1 prime and F2 prime are a pair of composable Quillen junctions. And we also have, as before, a cofibrant object X and a fibrant object Z in the target category. Then the following diagram computes. So the diagram looks like this. Sorry. Let's see here. Here we also have isomorphisms. Okay, so let us prove this statement. Although I did not formulate it, well, it is clear here what is the statement. So the first thing that we need to prove is that this phi large is compatible with homotopy relation. And the second part that we need to prove is that if we have a pair of composable adjunctions, then we have a commutative triangle of this sort. Okay, so first we observed that if we have two, say, right homotopic maps, then their images under the adjunction isomorphism are in fact also right homotopic. How do we prove this? By definition, right homotopy, existence of right homotopy means that there is a diagram of this form. And we just need to apply the adjunction isomorphism everywhere to see that, we obtain a diagram of this sort. And it remains to observe that f prime y prime is in fact a path object for f prime y, because a path object is defined as a factorization in the following diagram. So here we have a weak equivalence, and here we have a fibration. But since y is itself fibrant by assumption, that means that f prime preserves, since f prime is a right equivalent functor, it preserves fibrations. So in particular, the map from f prime y prime to f prime of y times y is also a fibration, and f prime preserves with equivalences in the subcategory of fibrant objects. Fibrant objects here. Because we have Ken-Brown's lemma, which implies that since it preserves all trivial fibrations, it must preserve weak equivalences in the subcategory of fibrant objects. So this diagram yields a right homotopy between the images of these two maps under phi large. And in complete analogy, if alpha is left homotopic to beta, where alpha is a map like this, and alpha and beta maps between these two objects. Then their pre-images under isomorphism phi are also left homotopic. And the second part follows from the description of Hom sets in the homotopy category as quotients of Hom sets in the model category under the assumption that the left argument is cofibrant and the right argument is fibrant. So yeah, basically all we need to do is to prove that this adjunction preserves homotopy relation. Okay, so now let's move on to the second small part of this larger part dedicated to derived adjunctions. And let's discuss derived natural isomorphisms. So the setup remains the same. We once again have a Quillen adjunction. Then, oh, probably I should formulate this as a proposition of some kind. So I write it in here. So assume that we have a Quillen adjunction, then there are unique functions u and u prime. Functions such that given a pair of two left deformations of the functor f, so these are left deformations, u maps it to a natural transformation, well, natural isomorphism is really uk1, k2 between homotopizations of the functor k1 and k2. And in complete similarity, if we have two approximations on the right to the functor f prime, then they are mapped by the function u prime into a natural transformation u prime k1 prime k2 prime, which is a natural transformation between homotopization of k2 prime and homotopization of k1 prime. And additionally, this pair of functions u and u prime satisfy the following properties. So first, u and u prime are natural in both arguments. And the second condition is that for any map T between two approximations. So this should be a map inside of an over category of the functor f, consisting of all homotopical functors between m and n. So if we have such a map and a map in either direction between right deformations, which is in the under category, the functors going in the opposite direction, and then we have that this transformation between homotopization of these approximation functors is in fact the same as homotopization of this natural transformation. And in complete similarity, we have this for right approximations. So let me prove this. As usual, I will prove only one half of this proposition, namely for the function u. And the rest can be deduced by inverting arrows. Okay, so consider composition. So we have this over category of homotopical functors over F, and we have a forgetful functor into the category of all homotopical functors between M and N. And then we have the homotopic category functor, which just goes to the ordinary functor category between homotopic categories of M and N. So U is a forgetful functor. And the functor HO sends weak equivalences, that is natural weak equivalences between homotopical functors to isomorphisms. And thus we have a factorization of this composition. Well, actually, we have a unique factorization, and that's just from the properties of homotopic category. And so this factorization looks like this. Well, now knowing that we have this factorization, we can define U to be the function which sends pair consisting of two left approximations. Two natural transformation between images of these two pairs under the localization functor. And so so this U satisfies all the requirements so it satisfies all the requirements for U we gave above. Yeah, so one question might be, where does this map between two approximations come from? Well, by definition, a left approximation is a homotopically terminal object in this category, which means that between any two homotopically terminal objects, there is in fact well, a homotopically unique map, which becomes unique when we pass to homotopic categories, which is precisely this transformation between images and the localization functor. Okay, so we've constructed such natural transformations between pairs. Now, yes. Now we can define what is a derived adjunction. So assume once again that we have Quillen junction. It looks like this. Then there is a unique function which associates to every pair like this. It's a pair consisting of the left and right approximations of Quillen functors. So it associates a derived junction which looks like this. So what are the properties of this function? Well, the first property is that it agrees with the derived nature of isomorphisms that we defined earlier. So assume that we have left approximations and also two right approximations. Then the derived nature of isomorphisms conjugate with respect to associated derived junction. So we have initial transformations like this. And they should be conjugate with respect to, well, if you want unit and co-unit of that junction. So we have derived junctions that look like this. And we want this isomorphisms to agree with these junctions. So the set for every left deformation of M onto the category of subcategory of cofibrant objects, and the right deformation maybe this larger Q here, and the right deformation R prime S prime from N to the full subcategory of fibrant objects. The junction isomorphism with the derived junction. So we have this just by composing our Quillen functor with the deformation functor. Yeah. So the adjunction isomorphism of this derived adjunction associated with this particular pair of approximations, namely FQ Fs and F prime, R prime, F prime is prime. So yeah, so this isomorphism assigns to every pair of objects x and m and y n the composition which looks something like this. So phi is partial adjunction isomorphism defined earlier. No, this all works because we pass to the subcategory of cofibrant objects here, and this is a fibrant object. And so we have this partial adjunction isomorphism, and the adjunction isomorphism which comes from this direct adjunction should be the same as this composition. Yeah, and other isomorphisms are induced by S and S prime. Okay. And so before proving this thing, which I should also call proposition, let me derive a short rollover. So assume that we have a Quillen adjunction. and assume that we have a pair of approximations well, then the functor, the homotopization of the functor k is an equivalence of categories if and only if the homotopization of functor k prime is an equivalence of categories. Okay, and also let me now state the promised result about compositions of Quillen functors and their relation to compositions of direct adjunctions. So that should be the proposition. So assume that we have Quillen adjunction number 1 and Quillen adjunction number 2, which are composable. And assume that we have a left approximation of F1, a left approximation of F2, and in the other direction, a right approximation of F1 prime and the right approximation of F2 prime. Then we have the following topology of functors. So the composition of this adjoint pair is exactly the same as the adjoint pair that comes from first taking the composition of homotopical functors and then descending them onto homotopic categories. And yes, so that's the statement. Okay, so first, well, let me enumerate these two propositions. So that'd be proposition number 1. This thing here, proposition number 2. So proof of the first proposition. Okay, so First, assume that we have just an adjoint pair in general between any two categories. And assume also that we have a pair of functors which go between the same categories. I also assume that there is a pair of natural isomorphisms. So one from G1 to G2, and the other one between G2 prime and G1 prime. Then there is a unique conjunction which includes these two functors. And such that H and H prime are conjugate with respect to these adjunctions. Okay. So the second part is that so we made this observation now. This is sufficient to prove that for any two left deformations of M onto a subcategory of cofibrant objects and any two right deformations if I'm on top of a subcategory of fibrant objects, the derived natural isomorphisms, which we defined earlier using these two functions. Yes, so these derived natural isomorphisms a conjugate with respect to the direct adjunctions which are given by these approximations. So we should show that these isomorphisms, the conjugate with respect to yeah. So to show that these isomorphisms are indeed conjugate, we consider the following diagrams. We have composition of these two deformations. We have a commutative square like this. Extension seems to hold. Okay. So here we take compositions like this. And we also have a dual commutative square, which comes from right deformations. And the commutativity of these squares implies that, in fact, we have sort of common deformations between two. So we have deformation here, Q2, Q1, as QS1, whereas 2S1 is the composition like this. And in the same way, we have common right deformation. So this thing here also deforms M into MC. This thing here deforms N into NF. So this implies that we have, in fact, we have the following isomorphisms of functors and the same thing for deformations. Now it remains to observe that we have for each pair of objects x in M and y in N, we have a commutative diagram of the following form. So so the rows of this diagram were described earlier, where we stated that for right and left deformations we have an isomorphism of Hom sets which involves partial adjunction. So here arrows look like this. Yeah, here arrows, it's in the opposite direction. So the main idea here is that for any two deformations, we can find sort of common refinement, which then affords us the required isomorphisms. So this is more or less what we wanted. Okay. So now let's prove the second proposition, which states that the composition of derived adjunctions is the same as the derived adjunction of the composition. So as we established just a moment ago, it is sufficient to consider only one pair of right and left approximations. No, well, yes. So we consider, I'm sorry, not the choice of approximations, but the choice of right and left deformations of M into MC and N into NF. So assume that R1 S1 and R2 S2 deformations of, so have a deformation like this, that's R1 S1, and we have a deformation like this, that's R2 S2. And also dually we have R1 prime S1 prime, which is a deformation of M to NF and R2 prime is 2 prime, which is a deformation of M into MF. Sorry, P into PF. Then that object of M, Z is some object of P, and since S1 prime, S1 is 2, S1 prime is 2 prime are natural, we have the following diagram, well, the following commutative diagram, which basically implies the required proposition. So let me write it down. It will be a very, very large diagram. Sorry, I'm almost finished. With this positive diagram. So we have something like this, and if we look carefully, it implies that, well, we have an isomorphism between the desired home sets, which means that we in fact have that in fact the composition of derived adjunctions coincides with the derived adjunction of the composition. Okay, so let me return. Return to the normal state. And this proves the proposition. Okay, so that's basically it for derived adjunctions of Quillen functors. Now I want to discuss Quillen equivalences. So the notion of Quillen equivalence is basically a notion of equivalence of homotopy theories. So one way to put it is that Quillen equivalence is such a Quillen adjunction that it induces an equivalence of on homotopy categories. However, it is something more than merely a functor between homotopy categories, which is an equivalence of categories, in particular because there are such model categories that they're well, that there is an equivalence between their homotopy categories, but it does not come from equivalent equivalence. So Quillen junction, Quillen equivalence is something more. And now I will discuss in detail what does it mean. So one way to put it is that, well, in terms of homotopical categories, is that if we have Quillen junction, then this junction is a Quillen equivalence. If for any left approximation and right approximation, we have mutually inverse homotopic equivalence of homotopical categories, meaning that their composition in two different orders is naturally weakly equivalent to the identity functor. Okay, so we have the following proposition, which characterizes Quillen equivalences in several different ways. So let f of prime be Quillen junction. Then the following assertions are required. So first one being that the thing that I stated earlier, that if I have the left approximation and the right approximation, then K and K prime are mutually inverse homotopic equivalences. The second assertion is that, well, it's a variation of the first one, so we just state sort of one half of what we stated previously, namely that we have, if we have any left approximation of f, then K is homotopic equivalence. So two primes is just the same thing, but for right approximations. The second condition states that there is a pair of approximations such that the homotopicizations future the universe occurrences of categories. This in particular implies that for any left approximation and right approximation, this is the case. Just because all left and right approximations are weakly equivalent as functors, and thus when we pass to the homotopy categories, they become isomorphic, and hence there are also equivalences of categories. As you can probably guess, variation of this assertion just drops the condition that there is right approximation, and we say that there should be left approximation such that its homotopization is an equivalence of categories. And two primes is just the same, but for right approximations. Okay, so this is all pretty obvious from the characterization that we gave earlier for direct adjunctions. Well, from the description of direct adjunctions. So I'm not sure that I even need to prove here anything, but yeah. But now I want to state a useful condition under which Quillen adjunction is equivalent equivalence. So something called Quillen condition. So once again, assume that we have a Quillen adjunction, and we say that this pair satisfies Quillen condition if for any pair of objects where X is cofibrant in M and Y is fibrant in N, a map from Fx to Y is a weak equivalence in N if and only if the joint map is a weak equivalence in M. And this immediately gives us a corollary. So assume that we have three composable Quillen adjunctions. then basically the class of Quillen equivalences inside of all Quillen functors between model categories satisfies 2 out of 3 property, or 3 for 2 property, if we use this custom terminology. So we consider 3 compositions. So if both these pairs are Quillen equivalences, then the original three functors are Quillen equivalences as well. Okay. So what we need to do is to prove the proposition. Yeah. So we need to prove these 2 propositions. Let me once again give them some notation, give them some numbers. So this will be proposition number 1. This will be proposition number 2. So I want to prove them, and first we observe that a functor is an equivalence of categories if and only if it is a part of an adjunction where unit and co-unit are natural isomorphisms. Now we can derive now we can derive both these propositions from the statement that we proved earlier, namely that if we have an approximation from the left and an approximation from the right, then for Quillen adjunction, obviously, then homotopisation of K is an equivalence of categories if and only if the homotopisation. Additionally, we will need the following proposition. Which looks like this. So, as usual, assume that we have Quillen adjunction, and assume that there is a left deformation of M into MC and the right deformation of into n. Then the following are equivalent. So for every pair of objects where X is cofibrant in M and Y is fibrant in F, a map like this is a weak equivalence in M. Is a weak equivalence in M if and only if its joint is a weak equivalence in M. Second is that the zigzag natural transformations which looks like this. For right deformation. Zigzag looks like this. So here, for example, this map is an adjoint the natural equivalence of the form like this. And so the zigzag natural transformations is in fact the zigzag of natural equivalences. That's the second assertion. And final one is that the unit of the right deformation per unit, which is a natural transformation between the identity functor and the homotopy category, and the composition of homotopizations of approximations. So yeah, and the co-unit is obviously in the other direction. So co-unit or unit should be a natural isomorphism. Okay, so let's prove this proposition. Observe that the first point implies the second one. The zigzag is of natural. If we see that, equivalences are reflected by the adjunction for cofibrant and fibrant objects. Now, note that after passing to homotypic categories, this zigzag is mapped precisely in is mapped to the unit of the adjunction. So this natural weak equivalence basically disappears, and we have an arrow in the direction of transformation from the identity functor in the homotypic category to the composition of derived adjunctions, which is, as we know, the same as the derived adjunction of the composition. Which means that if this zigzag consisted of natural equivalences, then the unit transformation is an isomorphism. Finally, we need to show that the third point implies the first one. So assume that, P is such a map in M that its joint map in N is a weak equivalence. Then there are several consequences of this. So first, the map of this form in M is also a weak equivalence. Which implies that after localizing this map, we're mapped to isomorphism in the homotypic category of the model category. Second observation is that the joint of this localized morphism. Is precisely the image and the localization of well, the joint morphism. So, and the model categories. And so the third observation is that joint gamma of f prime is prime y t is the composition of unit which by assumption of the point 3 is an isomorphism. But the image of gamma prime QFSX under the functor like this, which implies that it is an isomorphism. And finally, since M is saturated, meaning that under localization only weak equivalences are inverted, the map f prime s prime sub I is a weak equivalence, and this implies that the original map P, which went from X to Fy, is also a weak equivalence. That the third point implies the first one. Okay, I think that we've finished the topic of Quillen equivalences. Let me stop the recording.